So let's see. Welcome. I guess let me first, just in case there's anyone who wants to join, who's for some reason, I'll just go ahead and post the Zoom link there. Who cares? I think it should be all right. Okay. So what I wanted to do was, talk a little bit about Salsa and especially dive into this this PR that I have that kind of reworks, or is it a PR or is it just a branch? Maybe it's just a branch. I thought I made a PR from it, but I don't see a PR from me. So, okay. That reworks how the code is implemented, because if you're interested in helping hack on Salsa, there's no reason to learn the old code. So I think the new one is better. And it's not, this is not, so just to put it in context, I guess, before I start, let me pull up a HackMD here, first of all. And I'll send the link here. So yeah, let me just step back a second and give the big picture. Right. So I think where I would like to get us to is that we have this newer entity system that some of you may have seen or seen the work we've been doing there, and that we have a sort of a runtime that allows you to easily run work in parallel, sort of Rayon style, maybe, I don't know, Rayon-ish, and well, that's it. Those are the big ones, and it's efficient and everything. Oh no, there's one more thing, and handling fixed point cycles more, or handling cycles better, including fixed point. And I'll explain that in a second. I think in terms of what I hope is that I hope Salsa can become used by not only Rust Analyzer, but by Rust C and other compiler-like applications where it makes sense, or just in general applications. But I think in order to get used by Rust C, especially, that may not actually make sense, because Rust C is very different from Rust Analyzer. It's like a batch compiler. It has different optimization strategies. It needs to persist to disk. That may want to be its own crate, but hopefully one that's compatible with this general Salsa philosophy. Or it may be that we can extend Salsa in place to do all those things. But that's kind of the big picture where I'd like to see it go, is highly usable, convenient, and supporting parallel, and kind of more opinionated than it is now, like, so that it's more of, this is the way you do it, and if you do it this way, it works out nicely, versus the current API was aimed for flexibility in a couple of ways that I think are not necessary. That makes sense. So let me talk a little bit about fixed point cycles. Fixed point cycles, the idea is today when you have a cycle, it's just an error, although we have this recovery mechanism, right? So if you have a query that depends on another query that kind of circles back to itself, we allow you to recover from that with some default error value, essentially, but that's about it. And in practice, especially in Rust C and other compilers, that's not often good enough. Often you need to have more of the ability to say, well, here's a starting value that you can use, and then for the value result of that cycle, and then I'd like to run again and again until I kind of reach a fixed point. So an example would be like, well, an example might be if you were searching through a tree to see whether something is send or not, like all the fields reachable from a data structure, you can wind up reaching yourself again, like you have a linked list and it has a link to another node and then comes back to itself. And that's okay. We should be able to handle that. So if we want to make queries for each of the parts of that search so that we can get better incremental reuse throughout the search, we need to tolerate cycles. I'm not going to go into that in detail. I just wanted to kind of explain what it was. And that's, I think, probably one of the next set of PRs or things that I'm trying to work on is extending the cycle handling to cover that. But I did recently land a big PR that refactored the cycle handling in anticipation thereof, which I didn't plan to talk about, but we could, if I can find it somewhere. Anyway, what I did expect to talk about today is another little piece. Let me share my screen, which is really like the core algorithm of Salsa, essentially. Let me just get a poll. How many people, I realize I have no idea how familiar you all are with how Salsa works. So how many people feel like they understand the idea of Salsa, if not the way it's implemented exactly? Okay,
Not the idea.
All right. So
Rick and I are pretty used to using Salsa as consumers of the library, though we haven't hacked much on the internals.
Okay, cool. So I will just go over that real briefly. I assume that everyone's kind of follow, and you can tell me if you don't follow along. But right, you have these queries. They invoked on a set of keys, and they produce a value. And then you have inputs, and inputs are set on the outside. And so you can build up a dynamic graph where you have like, ooh, I could even do this. Let's see if I can remember how it works. Oh shit, oh, forget it. Try that. I can never remember the syntax for these other ones. Where you have like input, and then maybe there's some, what's the usual example? Let's call it, there's the source text for the compiler, and then there's like the parser, which consumes the source text. And then the AST creation, or something, right? And then the type checker. And when there's a change in, say, the source text here, that'll rerun as much of this as it has to until the result is the same, right? And then it kind of cuts off the re-execution. So that's how it feels as a user. And what I wanted to go over today was the way that's implemented and the algorithm and all the little annoying aspects to it. Like, among other things, we support multi-threading, so there could be multiple threads trying to run a given query at a given time. And how do we manage that? And the making sure that they coordinate with one another and don't mess things up. And how do we determine when something has changed, might need to be re-executed? So I did a diagram that I'm super proud of. Let me find it. That I'm going to work through here. Here it is. Come on, it's super nice. It's too small to even hope that you're going to read it. That's okay. But it's there for later digestion. But the basic algorithm, or the basic, well, first of all, any questions on this part? Feel free to just interrupt me if you have a question. So I'm realizing I haven't really planned how I'm going to explain this. So let me start from this. The basic data structure that we have in Salsa is this derived queue. Derived structure. And the idea is that stands for a derived query, meaning a query whose results are derived from inputs. It's a pure function of its inputs. as opposed to an input query, which is different, or a memoization query, or not memo, interning query. You can ignore those for now. We're just going to look at these these are the workhorse. So all of these queries, parser, AST creation, they'd all be derived queries. And that's what this illustrates here is the flow when you actually execute a derived query of what happens. But let me take you into the source. This is, as I said, I'm just going to walk through the new source. I'm not even going to try to compare it to what's done today, because I don't think most of you are familiar with what's done today anyways. It wouldn't be helpful. And it's here. Let's throw this link in here. So the derived storage is saying, what is the storage we need in the database for this query? And it's defined by this queue, which is like a type that implements the query function trait, and this memoization policy, which isn't that important. And you see that it has various fields, right? The group index, well, the database is going to be like your actual database struct has essentially one, well, it just has a big bunch of fields, one for each query in your system that are equal to these derived storage. So this group index is kind of part of this routing system, which I'm not going to go into right now, but we'll get to it. But that's the way when you execute when you have dependencies between queries, as we'll see, they each get, we kind of store an integer that has a group index and a query index, and that we can route back to the right table. Come back to that. The LRU, that's used to track LRU storage. I'm also going to skip over that, except to say that that's basically a mechanism for making sure that you have at most n entries in a table to avoid wasting too much memory. And the key map and the memo map are more interesting. So what the key map says is we have to map from the arguments, right? Each of these things actually has some arguments. Oops, that's not going to work. And we need to map from those to a unique integer, because integers make our lives easier. And that's the role of this key map, is it's going to map from the arguments, the actual values in the arguments, to a unique integer. And what I will say is, in the newer Salsa that I'm trying to move us towards this entity system, the arguments to queries are almost always themselves a unique integer. So this map is just an identity function. And the query arguments are entity IDs, which are unique integers. And so this is an identity function. But in this version of Salsa, as it is in this branch, it doesn't have any optimizations around that. So this is really an actual hash map. So the idea is that we're going to see when you start sort of saying, let's see. So you've got your start node. Your start node is like somebody did query with key 1, key 2, let's say, right? 2 arguments or something. The first thing we're going to do is, maybe I should not do this in GraphViz. That's probably going to get old real fast. Let's do it like this. When we start with doing a query, the very first thing we're going to do is we're going to map key 1, key 2 to an integer with the key map. I'm not. So from now on, which we'll just call k. So from now on, whenever after this point, we just have this integer, and we can work with that. And that's what we call a key. one thing you'll note is, when do you remove things from this map? The answer right now in this version of the code is we never do. So if you had a constantly growing set of keys, that would be a problem for you. So far, it hasn't seemed to bite people too much in practice, but that is something that I think works better in the entity system later on, because we actually have a sort of an answer for that. So far, makes sense.
That's the key in turning part, right?
Sorry, the key in turning part? Yeah, the key in turning. So it's just the keys. They persist forever. Because it's basically, we have these, we don't know otherwise when to get rid of these indices. Okay, the memo map and the sync map are the next two things. So the memo map is the most interesting part. That stores, well, I don't know if it's most interesting. It's one of the most interesting. It stores a map from the key to a memoized value. So it's saying something executed. We completed this query in the past, and we got a value out of it. So this identifies the value, the result, and what dependencies we needed to compute that result, along with durability and some other stuff, which I think I will gloss over at first. So let's take a look at that, actually. We can jump back to, let's open this, the memo rs file. So here's the memo map. So derived key index, that's this integer I was talking about. That's the unique integer. And you can see it's a dash map, which is like a concurrent read-write lock map. From that to a memo, arc swap, we'll talk about arc swap in a second. A memo map is, or sorry, a memo has the value and which revision it was verified at, and this is the dependency information. So there's a couple things interesting about this structure I want to point out. Which is that the memo, if you look here, you'll see, well, what arc swap is it's basically like a cell that wraps an arc. So it allows you to change. Once we get a handle on an arc swap, we can kind of get and set the arc that's inside. But the important reason I'm bringing that up is that these memos, so every time we complete a result, we store it in an arc. And you'll note that like most of these fields are not mutable, right? The value field and the revisions field are immutable. But the only one that can be changed after the arc is created is the verified at, which has an atomic cell. So the idea is kind of that we've got this cache. When you start to do a new thing, you start running. And at the end, you stick it in the cache when you get the result. And then when the next person comes, they see it in the cache, they can just use it. And it's that value is going to be, anytime you see something in the cache, you know that it's not changing under you, so you can make borrows and iterate over that value v and so forth in convenient ways. If it should happen that what will happen next is in the next revision, after there's been some changes to the inputs, we might need to recompute the memo. In that case, we'll re-execute, allocate a new memo, and replace the old one with a new value. Right? We don't update it in place. So they're kind of like a persistent data structure. That's a little different than the old architecture. We used to update them in place and things got really hairy. So basically, memos are a record of a value that was produced along with its dependencies. They are not changed once they are first created. We just make new ones. And the last thing is the sync map. So the sync map is meant to, if there are multiple threads, oops, I'm in the wrong file. If there's multiple threads, the role of the sync map is to coordinate between them so that only one of them is executing the query at a time. That is actually something I plan to change as part of the fix point, and I think could just be useful in general. Like, it's not obvious why you have to have only one query or only one thread execute the query at a time, because queries are idempotent, or I mean, like, you can run them many times, they'll just produce the same value as one another. Hopefully they should, or else there's something funky going on. But a lot of times it is useful because it's just a waste of effort. And if it's an expensive query, like running the type checker or something, you might not want to do it more than once. So you sort of want the option to synchronize, but you don't necessarily want to always have to do it. And for fixed point cycles and stuff, I think at least I don't know how to make it work. It gets a lot more complicated if you have to spread them across threads. It's much easier if you can keep them within a thread. So I would like, although this current version of the branch always synchronizes, it's designed to make that optional in the future, which is partly why this is the synchronization map is separated out. So now we have all the pieces. The high level phases is like, first we get this integer k. Then we look in, or we check the synchronization map to see if somebody is already executing this query. If so, we block for their answer. And if not, we check the memo map to see if we have a cached result or a cached memo M. If so, we check if M is up to date. And the fastest way to check is we say, well, we'll get back. I just want to give you the high level view. So we check if M is up to date. If it is, we return the cache value. Otherwise, we re-execute the function, create a memo, insert it into the memo map, and return. Right? That's the high level, and then we're going to sort of dive into these in a little more detail. So far, so good. So how do we check if the memo is up to date? Let's look at that. So each memo has a verified at field and a set of dependencies. We saw them here. Or we call it, I guess, the revisions. So what verified at, first of all, tangent revisions, maybe you already know this, but just in case, the way that we think about changes is there's a single integer associated with the database that we call the revision. Every time you change an input in any way, we create a new revision. So it's always linear. So they can sort of say, okay, it's like a timestamp, right? We start out in revision 1 or 0 or something, and then make a change. Now you're in revision 1, now you're in revision 2, 3, 4, and so on. So we always have, each change to inputs triggers a new revision, always have a current revision R. And the only thing I'll say is we use the and mute self guarantees to ensure this, right? So in order to make a new revision, you have to have an and mute hold on the database, which means there can't be multiple threads going off and starting new revisions in parallel. So there's always like a well-defined notion of one revision, what revision you're at. So the verified at field stores a revision. And it's an atomic cell, so it's mutable, which is useful. And the idea here is this is basically just to save a lot of work. When a memo is first created, verified at is set to the current revision. So that's essentially at that point, it's just saying this is when it was computed. And so of course it's up to date now. If you never make any more changes to the input, you never have to check anything because it couldn't possibly have changed. So the first thing we're going to do, actually here, I'll pop over to my crazy diagram and try to show you in here. the first thing we do is we load the memo map. I guess that's interesting. I was a little bit wrong, I guess. I guess we claim the sync map later. Ah, yeah. I think that was on purpose. I remember that now. So this isn't exactly right. The first thing we do when you do a query is we check to see if we have a cached memo. And this was exactly because why synchronize? If the result is already there and already memoized, we don't want different threads to have to block on one another. That's like an unnecessary lock. I'm really shooting for, my real hope and goal is that we can get this path, this hot path, to have no locks at all, no writes. That's not exactly true today because the dash map has some internal locking and so forth. But if you ignore that, it is true, I think. And there are data structures like concurrent hash maps and things that don't do locks on a successful read. But I don't know if they're actually faster. I think the reason dash map uses locks is it turns out it's pretty good in practice. Anyway, so the very first thing we do is we look and see if we have a memo. And if we do, then we can check, is it the current revision or not? And if it is, we can just return it, right? So this is like the ultra fast path. And in this newer version of Salsa, we do something interesting that isn't exposed to the user yet. But we do leverage it in the entity version. Let me try to find it. So the code corresponding to that read is right here. Oh, I guess it's not in this. Well, anyway, so this function fetch is the one that gets called when you actually try to do a read. So it's really called fetch. Dot fetch, you can think of it. And I guess it doesn't do it in this branch, but what we can do in the memoization code is actually have an ampersand here. So we're returning a pointer into that memo. And that way you don't even have to clone the value on a successful path. You just hold a reference to it. And the way that that works is a little bit of unsafe code, which I won't talk about. The first unsafe code in Salsa. So it's a little sad, but I think it's worth it. And so the idea is essentially, and that's part of when I made this whole big deal about memos being immutable once they're created, is it kind of leverages that. So as long as we can guarantee that the memo isn't freed until the next revision, it's safe to have a pointer into that memo that lasts as long as the and self that started it. And you can't make a new revision until you drop that and self on the database because you need an and mute on the database to do it. So it all works out, which is kind of cool. But for now, we clone it, I think. Doesn't matter. So if so that's the easy path. It was created in the current revision, or at least we'll see it. It could also mean we've already checked it in the current revision. That's easy. But otherwise, we have to go and do a more detailed look. And actually, this is like a bit of an optimization. So I'm going to skip over this durability thing for the moment. But what the durability is basically a way for us to say, rather than iterate through all the dependencies one by one, if we recognize that some inputs change less frequently than others, we can assign them a higher durability. The user does that, tells us these are less likely to change. And so then we might be able to skip if we can say, oh, like the high level idea is like Rust Analyzer says, I doubt the Rust standard library is changing anytime soon. So that has a very high durability. And then if you have some query that all its inputs came from the Rust standard library, even if the user changed their code, we don't need to recheck its inputs because that would be a waste of time. So that's what this is meant to do. So this is another fast check, but I'm going to ignore it for now and say, okay, we got to do the slow check. We have to go and actually figure out if any of our inputs have actually changed. And then we would have to re-execute. And at this point, we have to start synchronizing. So we claim the synchronization map. And by the way, this diagram, like each of these things, corresponds to a piece of the code, right? So this quick check I talked about, I call it shallow verify, lives somewhere. maybe in fetch. No, I don't know where it lives. Can't remember. Here, shallow verify. Yeah, and you can kind of see it corresponds pretty closely. So it checks if the revision, it loads the revision out of the cell, checks if it's equal to the current revision, otherwise checks the durability or returns false. So this does the shallow. This is the hot, this together is the hot path, or at least what I hope is the hot path, or else you got problems. And then goes over here to actually claim the lock. And for now, let's ignore this path and just say, assume we're able to claim the lock. And the lock is not a, when I say claim the lock, I don't mean a like mutex in the traditional way. I mean, there's a map from your key to your state, right? And if there's an entry for your key, then somebody has the lock. And if there's not an entry for your key, then nobody has the lock on that key. So it's more like a file system lock or something like that. And so claiming basically calls .entry, and if it's vacant, nobody has the lock, we can insert a state saying, hey, this is my ID. I'm working on this key right now. And we have a little flag that people can set to true if they want the result. So when others are blocking on us, we find out. So this relies on, this part here is building on dash map. Like you don't see the lock, but that's because it's built in to dash map. There's a kind of lock that makes all of this happen atomically. And at the point where we call entry.insert is where the lock gets released. So we acquire the lock when we call entry, and then when we call entry.insert, we kind of lose it. So if there are multiple threads trying to claim at the same time, they're going to get linearized in some order. That makes sense. So right, that's the synchronization map. And then this is the part where I left out. So now it's, if there was a memo, iterate over the inputs. So the next thing we have to do, to go back to our, what's the right? Well, we'll just use this one. There's a nicer example that I can't remember off the top of my head right now that I usually use to explain this, but right, if we found, basically what might have happened is we changed the source text. So in revision 1, we set the source text and we executed. So all of these nodes, let's do this. I'm going to walk through an execution now. We're gonna start adding in a little more of the state with what we've seen so far. So in the very beginning, we set the source text, and we didn't have any of this other stuff, right? So we set the source text to be whatever the first version of the program was, and that created revision 1. And then we invoked the type checker. The type checker said, I need an AST, so that invoked the AST query. The AST query said, I need to parse it, so that invoked the parser. The parser read the source text, created whatever the parser does, which then was used to create the AST, which then was used to run the type checker, right? And I guess that's, I'm just gonna, I'm gonna cut this node out because let's say the parser makes the AST. Why not? I don't think it's important for anything. So now that's the data structure we have. Only like that's sort of the set of memos, but each one of these is going to have a little extra data, right? I'm not going to get too fancy. So this parser actually has also verified at. Okay, I'm going to get fancy. I might regret this. But it's going to look so cool. You have to look at the rendered one. because this is going to be unreadable. So this is the parser. Okay. So we've got the verified at field for this. And then the type checker also has its own verified at field, right? And we're all in revision 1 and everybody's happy. And I guess I left out one other thing, which is the source text. We didn't talk about this, but of course the inputs have their own data, and they have their own sort of, it's called changed at, because we don't have to verify it. We just know when the input changed and when it didn't, but they have their own little field, right? Oops, what is this nonsense? Okay, so now that's revision 1, and then a change happens. And so changed at is here. Now we're in revision 2, right? And then we're going to call the type checker. So first thing we're going to notice, the verified at is out of date. It's not the current revision anymore. And the durability check fails. So we get the synchronization lock. And we start walking the inputs. Each of these edges, which we're going to see are stored in a list. And we'll invoke the same function on the parser, which will in turn go and check its input and see that it's changed, right? And so this check is going to return that the parser has altered. So let's kind of walk through the code that does that, I guess, and then it will re-execute the parser. Does this make sense? One thing I realized might be a little confusing is I'm drawing nodes here, but the way that it's stored is like for a given query, the hash map, each of these nodes is one entry in one of those hash maps. Okay. So let's see. Right, we were going to walk through the code that does this. This is looking really messy. I have to adjust what's in front, I think. But the code is here. So it's going to be maybe changed after.
Question.
Oh yeah.
What is the granularity of the dependency information that's stored on each query? Is it like query plus key? So you know this query depends on that query called with these arguments? Or
Yes.
Okay.
It's exactly that. So right, this, where is this function? I think it's called, there it is. Yeah, we can talk about that. So what's in these, let's look at the structure of the dependency information. So the memo stores a field called query revisions. And what is that? We haven't actually looked at that field yet. That's found in this other crate for some reason, or this other module. There, which is here. So what does this have? This has a kind of summary of what is of all the inputs, when is the most recent revision and which one of them changed, what was their minimum durability. That's not so important. But also, what is the full list of inputs, which is down here. And it can be one of 3 things. I think I simplified this in my some other branch where I got rid of this one. This was just a mini optimization for saying when you have an empty list, don't allocate an arc for every empty list. That's kind of wasteful. But basically, you either have a list of known nodes, and yes, it's both a combination. We'll look at this in a second, but this is the combination of a query and a key, or you have an unknown set of nodes. And the reason for this is sometimes you have these untracked reads like volatile data and stuff like that, and you just kind of have to assume that it may have changed in that case because you don't know the full set of inputs. So that can be useful for integrating with like sources of randomness or other stuff that actually does potentially change on every revision. So let's
And then
assume
where's the durability stored that you were talking about?
it's up here.
Oh, sorry. Yeah, cool.
Yeah. So this database key index, first of all, let me copy a few links here. So this is how we store dependency information. There's so there's the query revisions struct that has summary information, and then the query inputs that has the detailed list. And each thing in there is called a database key index. And this is a pretty useful thing that it's probably the right time to cover. So a database key index, what is that? That is a 64-bit integer with 3 parts. So the group, the query, and the key. If you've written Salsa programs, you know that you make these query groups that are like a trait, and they have inside of them a bunch of methods, which are the individual queries, and those methods have arguments, which are the keys. Each of those things gets an index. We already saw how the key gets their index. There's a big hash map that maps from the like values you gave to some fresh index. The group ones are assigned by the order. When you make the database, you have to list all your groups. So we give each of them an index as we do that. And then inside any particular group, we give each of the functions an index based on the order in which they appear. And the macro that's generating them does that, right? That's the procedural macro. And so this way you can kind of route with this 64-bit integer, we can route from we can route all the way to an exact entry in the table. First, we look at the group index, and the database has basically a vector of groups. So the challenge here is that if you look carefully at the code, the place that generates the code for the database doesn't know the full set of queries, like by design. It just knows the names of the groups, right? The structs and things that represent the group, but it doesn't know what queries are in those groups. And that way you don't have to change anything when you add new queries in a group, which is good. But so it has basically a vector of groups, and it uses this group index to find the right group, and then it hands the rest of the index to the group, and then that group knows about its queries, so it can use the query index to find the exact derived storage or whatever that you're looking for, and then it hands the key index to the derived storage, which can use that to look up things in its map. This lets us make links between nodes. The other nice thing about it is you can make links between nodes without knowing their types. Right, so my query may read data of all kinds of different types that don't appear. If I had to sort of make a link to the actual type, it would be a memo, and the memo is generic over the key and value. So I'd have to somehow deal with the fact that every kind of key and value that I use inside my running code I'd have to give it a type. It would be very difficult. But now I can just call them all by integer and they know their own types. I don't need to know them for them, if that makes sense.
Does that mean that in principle you could dynamically generate new queries for a given group?
Yes. And I want to support that. I didn't mention that, but yeah, I think we should, it's sort of been designed with that in mind also, that you should be able to link in extra groups or extra queries. And the use case I have in mind is like procedural macros actually. So if for us see let's say we're linking in a new procedural macro, that macro might itself be based on Salsa and be able to integrate with our incremental compilation, and have its own group index and query index and stuff. I haven't really worked out how that would actually work, but in principle, it should work. So, right. So that's basically, at the end of the day, assuming it's not one of these sort of, well, where the heck was I guess I was here. Hold on, I'm actually getting some messages. Let me just take a second to see if there's something urgent. Nope. So at the end of the day, the inputs are basically, these inputs that we saw is essentially an arced array of these indices. So that we can easily copy them around. So when we, in this deep verify code, so the deep verify is after we've gotten the synchronization lock and we've decided that it might indeed be out of date and our simple checks didn't work, then we have to do the expensive checks. And the first thing we do is check the simple ones again, because in the time between us acquiring the lock or us doing the early check and acquiring the lock, somebody else might have come in and actually done the check for us. So it's always a good idea to double check. But then we basically just iterate over each of those inputs. And we call this maybe changed after function. And so what that is, so basically we say, so deep verify basically says for each input I in the memo, if maybe changed after I LV. So LV is the last, or let's call it LR. The last revision I was verified at. Right. So what we know is we read the verified at field, and we know that that field only gets updated whenever this memo is known to be up to date. So as of that revision, whatever it was, the memo was up to date. And the question is it still up to date? And the answer is, it is, so long as no input has changed since that revision when we last verified it. So we're going to ask, did this input I maybe change after the revision LR? And then we would say, if so, this entry is dirty, right? And if no inputs have possibly changed, then we can update the verified at revision to the current revision and return in memo is clean. Make sense? I hope.
I'm a little bit confused.
Good.
But I'm struggling to understand that last point. I'm struggling to describe my question. So I don't understand how there would be a new revision if no inputs have possibly changed.
Yeah, that's a really good question. Let's walk through our example a little more, and I'll show you how that could happen. So remember, we were here and we had modified the source text to be something different, right? And so we entered revision 2, and then we have these potentially outdated memos hanging around that came from the older revision. You're going to have to unmute and because I want you to check back with me, make sure that makes sense.
But so if we're at Parser, and Parser last revision I was verified at is 1, right?
Mm-hmm.
So I still don't understand. It says if no inputs have possibly changed.
Yeah,
Oh, I see. The revisions are per query.
well, let's walk through it from here. So we start at the type checker, or right, actually, and the type checker says, well, my verified at is out of date. So we can kind of add that in here. First, it says if it does the shallow verify, and the shallow verify says, is my verified at up to date? And in this case, the answer is no. And so we go down to the deep version. And we start iterating over our inputs one by one. In this case, there's only one. And then we ask the parser, did it maybe change? And it's going to recursively do the same thing. So it's going to say, no, I'm not up to date. Let me iterate over my inputs. I have exactly one. It's going to ask the source text, did you maybe change since revision 1? So far, so good. Nobody's answered yet, right? We just asked these questions. So we got a little stack going on. And in this case, it's a base input, right? And so when a base input gets asked, did you maybe change? It can answer definitively by just looking at its record of when it last changed. So it says, yes, I did change, right? And so it returns, yes, I may be changed. And now we're here, we're in the parser, we're iterating over our inputs. We see that some input may be changed. And so we consider the parser to be dirty. And remember, we still haven't answered the type checker yet. The type checker is still waiting to find out if the parser changed or not. So we're just looking at the parser right now. And what's going to happen, I haven't shown you that code yet, but is the parser is going to re-execute. So part of when you ask, did you maybe change after this date? It's actually maybe a deceptive question. It's not just saying, do you have any inputs that changed? It will also re-execute the parser, reparse, and look at the output. And it might be that all we changed in the source text was like adding a comment, and it has no effect on the result of the parser at all. And in that case, the output is the same. And if the output is the same, we can actually say, no, we didn't change. we can move our verified at up to this current revision and say, no, we have not changed. Even though some of our inputs changed because our output didn't, and that's all that the type checker cares about.
Okay, yeah, that makes sense. I just kind of was forgetting the case that something could output the same value based on a different input. Yeah,
that's kind of the whole magic. Like it's sort of the trick that lets Salsa be smarter than make or something. Whether it's worth it in the end is an interesting question, because sometimes it might be faster. It might be fast enough to just re-execute anyway. But I think it's cool, so we still do it. But that's the idea. And yeah, so then you can actually have the verified at get. Well, I think what we do actually is that we create a new memo. I didn't quite cover that part yet. There's a field in the memo that says when you last changed. And so if we re-execute, we will still make a new memo, because it might have different dependencies and other things. Like it might have gotten the same value, but through a different route this time. The computation might have been different, but the value is the same. And then we'll backdate, is what we call it. We'll take the changed at and move it to an older revision, saying, you know, this memo was produced in this revision, but the value hasn't changed since the older one. So I'm gonna backdate it. But can ignore that for the moment. So and this if no inputs have possibly changed basically means if this for loop completes without finding anything, then it's not like an extra check. It's just if the for loop exits normally. So if for loop terminates, then no inputs have possibly changed. So that's right here, right? Here's the for loop. It says, if I may be changed after, then I can return false. I failed to verify. Otherwise, I call mark as verified, which just sets the field and I think does a salsa event or something, and then return true. Okay. Any more questions on that so far? We've like almost covered the whole thing. But I know I'm zooming through, so I want questions because it suggests some of you understand. But, all right.
One question, one thing I didn't quite understand.
Yeah.
So you mentioned you could actually, you have to update the memo even if the value didn't change. How does that work exactly? How could the dependencies have changed if the value didn't? Or was I misunderstanding?
No, you were understanding. I mean, that's like, we're kind of about to walk through that part of the code. So maybe it'll be clearer if I just walk through it. But let me start with the high level idea, leaving aside like the mechanics, how the data is stored. Imagine, I mean, if the parser has the job of parsing the input, it also throws away some of the input, right? Like the source text might have a bunch of white space, and maybe they change the indentation on a line, but that doesn't affect the parser, which produces the same AST either way. So its inputs can change because it has a different input string. It's got more white space than it used to, but its output might still be the same. Another way to look at it is like the plus, you know, if one of your nodes is summing up a bunch of things in a list, and the individual values in the list might change, but their total might not. And so anything that only looks at the total doesn't need to re-execute.
Right. So if the source text contains some new information, the parser looked at it, potentially applied a query to it, decided that it wasn't important, the value didn't change. But if the same query that it used to decide that it wasn't important, if that would potentially change in the future, it needs to be updated, I guess.
Yeah, well, in this case, the way I'm thinking of it is the type checker just looks at the AST, and the AST just looks at the source text. So the idea is, does the type checker, you've made some edits to the file, do we need to rerun the type checker? Or can we skip it? We're always going to rerun the parser because you made an edit, the source text has changed. So the parser is going to rerun no matter what. But it might produce the same AST it did before, in which case we would skip rerunning the type checker. And that step that allows this to rerun without making its dependencies dirty, or its the things that depend on it dirty, and forcing them to rerun, that's this backdating thing that I'm talking about.
Makes sense.
Okay. So how does that work? Let's dig into it, and I think it'll get, I hope it will get clearer. So jumping back to fetch, this is the biggest, this is like the high level entry point. Oh, I guess compute value is what I want. Yeah, okay, well, so fetch is where it starts. It calls somewhere here, calls compute value. Compute value tries first the hot path. This is the one that just checks if the revision information is all to date, and if so, it just does a clone. Also calls the cold path. The cold path grabs the synchronization lock, pushes the query onto a stack of active queries. I skipped over that. I'm not going to go into it right now, but that's part of cycle handling. And then grabs the memoized value from the map, calls deep verify, right? And if deep verify, which is the thing we've just been talking about, iterates over all of the dependencies and finds them all to either be up to date or have produced the same output since last time, then you just clone the existing value. But if deep verify returns false, or there is no memoized value yet, then we have to execute the function. So that's where we are now. And in the case where we execute the function.
But either way, does it then create a new revision? Is that,
The revision was already created when you changed the input.
Yeah, okay, but it's just the value associated with it can either just be one that isn't recomputed or, yeah, okay. I think I get it now.
Yeah, so there may be an existing memo. And we're gonna, if we re-execute, we're going to make a new memo, but we still have the old one around and we can compare them and tweak their revision information. If that makes sense.
Yeah, it does.
Yeah. So execute is here. You'll notice it takes the old memo if there was one, as an option. But mostly, what does it do? Let me just do blah 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 blah. There's some cycle handling that I'm gonna ignore, continue to ignore, but it calls q : execute. That is an associated function defined by, so the q type is defined by the procedural macro, and it's like unique to your code. And so this execute is whatever code you wrote for this query. So this is really calling the query now and running its body. And that, let's just assume it's successful. That's going to produce a result. This is, of course, a recursive call. It might go make other queries. It can do all kinds of things. If it makes other queries, that stack I talked about, we're pushing this query somewhere. Where do we do it? I don't know where we do it. I'm confused, but I guess I overlooked it already somewhere. In any case, we push this query on the stack. That stack entry sort of accumulates the set of things you looked at in thread local storage, basically. Oh, I see. It's already been pushed before we came into this function. So the active query guard is the type that's saying, hey, there is an active query on the stack. So we're going to run this code. It's going to return a value. And then we call active query.pop. I see. That's right. And this will take it off the stack. This takes the query off of the, so there is a stack that's, I'm now realizing there's a part I didn't talk about, which is for every active thread, there's a runtime. The runtime has a stack. It's available from thread local storage. This takes that query off that stack and gives back to you the list of all the things, all the edges that it created, all the dependencies. So if it were the parser that we've re-executed, the parser read from the source text, that would have inserted an edge into this set saying, here's what you read. You read this base input. In that case, there would just be one thing in it. And then we run along and we say, okay, was there an old memoized value? Did it still have a value associated with it? If there was, we can compare with this memoized value EQ and see if the old value is equal to the new value. This is the backdating we've been talking about, the kind of complex bit. So we've rerun the query, we've got a new value, we're going to compare against the old value. And if the two are equal, we're going to update the changed revision. So instead of saying that it changed in the current revision, we're going to backdate it to whatever revision we had before, because apparently it hasn't changed. It still produced the same value. So we still have a new memo struct with a potentially new set of dependencies, and which is verified in the current revision, and which has, but it has the same value, or at least an EQ value, a value that is EQ to the old value in it. And so we can push the changed at to be equal to the old value. Then we insert this into the map. This is, at that point, we're done. We re-executed it. We've stored the value, and so we can just return it. This is just a clone of the value or something. And now if somebody comes later, they'll find it in the map and they'll start this whole process over again. But they'll find it, but the new memo that we inserted has a it's last verified at this current revision. So as long as no inputs, if someone calls this again in the same revision, it'll always be a hit. backdate. So if we, just to walk through this one, what would actually happen? Let's complete this walkthrough because it's a little bit interesting. What will actually happen is we start at the type checker. We discover that it might be dirty. We go back to the parser. We discover that it might be dirty. We go back to the source text. We discover that it is dirty. We re-execute the parser. And at that point, it's going to produce a new memo. I left out this field. Let's add this field in. So in addition to verified at, there's a changed at field in the memo that tells you the revision in which this last changed. So in the new revision, we're going to create a new memo. It has the verified, initially it has verified at 2 and changed at 2. So when you first make the memo, it always starts with the current revision in everything. But then we go ahead, I guess I'll add this in here too. It's also got the value. And let's say it's like, you know, whatever, something. And the type checker, maybe its value is just okay, or a list of errors or something. So initially, after we execute, we rerun, and it turns out these have the same AST, and so we compare them. We see that they're equal, and we set the changed at back to 1 to copy what it used to be, and then we replace this memo with the new one in the table by doing that insert call. And so that effectively, this part I realize might not be entirely obvious. Effectively, that creates this edge and sort of deletes these old edges like that. And we would, at that point, we return to the type checker and we say, I have verified the parser. It has not changed since revision 1. And this data is still out of date, but ignore that for a second. Does this so far make sense conceptually? And did this thing I said about the edge make sense? I'm guessing not, because I didn't really explain it.
That like the edge between the memos there, or
Yeah.
conceptually? Okay.
So the thing is that there is no edge in the memory. Like there's a conceptual edge, but actually this just stores the index of this memo in some table, right? So to actually, like, there's no direct link between the 2 bits of memory. This has an index and there's a database, and the database has a map from the index to this. So when we replace the memo in the hash map at that index, we've essentially redirected the edge now without mutating this structure at all. So it's the edges are, I guess there's a bit of a mismatch between like this diagram, which is kind of at the conceptual level, and then you have to map it to how it gets stored, which is totally different. It might be useful if I were to draw it in, but that'll take me too long. Does that make sense?
So essentially, every query plus key has an act, like the latest memo, and that is the ID.
Yeah. I'm thinking, well, maybe I can do it. Anyway, I might try to do it in a second, but let me just finish out before let's not get over rotated on this edge bit, because I want to finish the last thing, which is now we return false in the sense, or we return that we have not changed to the type checker. The type checker says, oh, okay, I've been through all my inputs. None of them have changed. All I have to do is bump my revision, and that's the thing that's in a cell, so I can do that without creating a new memo. I bump it to the current revision and I just return the existing value, and I never re-execute. And that's how it works end to end. Fiend. I don't know what else to say. That's how it works. There's, I guess there's like a little time left. I think I bracketed it in 90 minutes. So obviously feel free to ask questions, but we can also talk about where we go from here. But so I guess the question is, what do we do next? Like I said, I want to grow up a set of maintainers, and you all seem excited and interested, and I'm happy about that. Hopefully I haven't scared you off. My hunch is this, I went through a lot in this 90 minutes, and I'm guessing that if it were me, at least in your shoes, I would have to sit down with the code and actually debug a bug or make some changes before I would claim to really understand it. So don't feel discouraged if you think that's the case. I hope that one could compare what I said with this flow graph and try to map that to the code, and it will all make sense eventually. But I think, like, I have to turn this in terms of the next steps. I have to turn this into a PR. That's step number one. I would like to land this code because it's much different than the current architecture, and I think much simpler and kind of takes us to the next level. I have only one hesitation, which is that I haven't benchmarked it at all or done anything to really test it in production. So I think one thing I would love is if somebody who is familiar with Rust Analyzer, or actually, it doesn't matter. I would love if people would try it on their own projects, Rust Analyzer among them, but I think some of you work on other things that use Salsa. This, in theory, I think is API compatible with the existing Salsa, so you should be able to just grab, the git revision and build it, and see whether it works, first of all, and secondly, if it performs well for you.
This is the staging branch that you're talking about?
Yeah, so I'll open a PR, but I think I would love people to try it, see if it works, and how the performance is. I did try it on Rust Analyzer on some of the existing benchmarks, and I did not see a good result. I'm not exactly sure what I saw, but it looked like it was doing a lot more executions than it used to, which either means there's a bug or means something else. I couldn't quite tell, because the way that the test was set up, I think it was running Rust Analyzer on itself, and I wasn't entirely sure if the reason that it was getting a lot more re-execution was actually legitimate or not. So someone who knows Rust Analyzer better would probably be able to answer that. All I'll say is the test looked a tiny bit suspicious to me, because it was like, no, I can't remember why, but I felt like maybe there actually were more changes. Like, it was comparing against a code base that was not the same in both cases. But anyway, someone should look at that. That would be awesome. And if you're not working on Rust Analyzer, but you have other projects, same thing. If we had 2 or 3 people try it and things are working well, then I would feel pretty good about landing it, and we'll just go from there. If we find bugs, then that's a great to-do item, tracking down the bug and trying to fix it. And I'd be happy to coordinate that, and either we could do it some like live debug it, or which might be useful, pair debug it, so to speak, or people can try on their own.
We should be able to try it on our system. We should be able to get a pretty good performance estimate, as well as if there was any output change.
Cool. Are you using the parallel capabilities of Salsa?
Yeah, we are.
Okay, because I'm also curious to know how that performs. Like, I believe it should be better. So, I mean, it's doing much finer grain locking and things than it used to, thanks to dash map. and a relatively simplified architecture.
Is it still using the same parallel database API?
Yeah,
So you make a snapshot and okay.
I think it's API equivalent, as far as I know.
It should be pretty easy to test them.
I guess if it's not API equivalent and I've forgotten something, I'd like to know that too. But okay, cool.
There was an old PR somewhere, I can't remember what it was, for making allowing some of the queries to be async, so giving them futures. Would that be easier to do now as well, since it's a stack of things that or have you thought about this at all? Because I know it's not a super common scenario for particularly compilers, but I mean, even in our case, I mean, there is some context where being able to make async queries or like could be useful.
Yeah,
I'm just trying to picture it.
I have not really thought about it, and I feel pretty bad because that person, I think it's Marwez, I think, right? They did a lot of excellent work, and I haven't devoted a lot of energy to it. And now I'm coming here with the big PRs that are totally different, which feels like bad OS open source maintainer etiquette. So sorry, Marwez. But I haven't really thought about it. I think I've kind of been a little skeptical about async support because it just seemed like it wasn't clearly a win, and it would make the async support in Rust is still not totally there yet. So things like traits and stuff don't work so well, and it would just make everything more complicated to try and support it. But I am open to it. I guess I would rather, I think the order in which I'd like to do things is to first get it working the way we want it with synchronous support, with the new entity system and stuff like that, and then try to adapt it, rather than adapting it now and then having to like keep that complexity, you know what I mean, as we go. That said, I think the newer system, I'll have to think about it. The newer entity system in particular has a lot less traits than the old one did.
Yeah.
Because it doesn't, like in this version, everything, every query you do goes through the database trait. But in the newer entity system, they're actually direct calls to functions, just like any other Rust function. And it's just that the function reaches into the database to find its storage. So it's sort of wrapped, I kind of wrapped your function with a decorator, but which might actually change the ballgame a lot. I still think we're gonna want good async in trait support to make it really work. I guess maybe we can use the async trait crate or something.
Yeah, fair enough. But it might be good to at least make a mention of it.
Yeah, at least I should read Marwez's PR. I owe that to him. And see what approach he took. Maybe he had some clever idea that I haven't thought about. The only other thing I can think, I guess what I was just realizing is, in addition to assessing this PR, I did just land recently also, like what's on master has the new cycle handling, and that was also a pretty big rewrite from the old one. So maybe what makes sense is to first assess master and see if that's working. And if so, we could even issue a new release with that, and then land this and assess that. And if we wanted, we could do another call like this to walk through how the cycle handling works, because it's interesting to me. But
Awesome.
So that cycle handling is without the like fixed point stuff, or does that include some of the new changes for better fixed point support?
no, it doesn't do anything to point. What it does do is it fixes the recovery, which was pretty broken. And broken both in the sense of it would ice sometimes, or the equivalent of ice. It would panic, and that it just didn't make sense what it did.
Okay.
And so now it does the model now is basically you can assign a recovery value to any query. And if none of the queries that are participating in the cycle have recovery, then it will panic. But if any of them do, then it'll sort of break the cycle by giving them every function that has recovery gets that recovery value, and the functions that don't get their value based on, as if the recovery value had been normally returned. So that sort of breaks the cycle, which is much cleaner and lets you do some cool stuff. Plus the code is easier to understand because it has been refactored. But it doesn't yet do fixed point, but I think it's in a better place to be able to do fixed point which is sort of what I plan to do next. All right, so why don't we do that, and then we'll schedule another meeting to go over the cycle code. Thanks to all of you for joining. This is super fun. I hope we get a great Salsa group going. I will post this recording to YouTube, so if you want to watch it again, you can. Also, the HackMD is there, and I tried to do a good job of putting links. But let me know. I'm really keen to have Salsa well documented. So another thing I would appreciate is if people take a look at what's there, look at the docs and the flow map and all that stuff, and see if it's helpful, and if not, ask questions so we can realize how to improve it. Oh, one other thing. I'm also planning, this is sort of independent, but I'm planning, this algorithm, as you may have noted, is fairly complicated. And it feels like, not in a while, but it feels like every time I would do a deep dive, I would find some bug. So I have like about 90% confidence in its correctness. And so one of the things I'm also planning on doing is I've been talking to various people in the formal verification community and tinkering with like modeling the algorithm and trying to prove properties about it. So far, I haven't figured out how to do that in a useful way, but if I do, if any of you have experience in that, I'd love to talk about it. And if I do succeed, I'll try to show you. But
yeah, sounds really cool. I have, if I'm being incredibly generous, some experience, but
okay.
More just interest.
All right. Well, thanks everybody, and have a good day.
Thanks.
Yeah, thank you.
Thanks, you. Thanks.
Thanks, this was great.